Welcome to the latest Advanced High Strength Steel Insights blog. Today, we'll be covering the microstructural phases that are in low carbon steels and how these phases are responsible for the properties of your sheet steels that go into your manufacturing plants. Today's blog and others are going to be featured on ahssinsights.org, the leading online resource for technical information on the metallurgy, forming, and joining of advanced high-strength steels for automotive applications. This information is being brought to you by WorldAutoSteel, the automotive group of the World Steel Association. I'm Danny Schaeffler, President of Engineering Quality Solutions, a sheet metal formability consulting firm, and I'm also the technical editor for the metallurgy and forming sections of the Advanced High Strength Steel Application Guidelines. Atoms arrange themselves in three-dimensional patterns called lattices. Think about billiard balls in multiple layers. The balls can be one layer directly above the prior one, or they can be shifted and rest in the crevice formed by adjacent balls in the layer below. The balls are all the same material, but the gap size changes with different arrangements. In the simple example that's shown here, the atoms can arrange themselves in a square pattern or a triangle pattern. The atom size is the same, but the gap size, where small elements like carbon can fit in, depends on the lattice arrangement. And this is what happens with steel, which for most automotive grades is 97% iron. As the steel cools from high temperatures after hot rolling or annealing, the atomic orientation known as austenite is stable. Up to 2% carbon can fit into this arrangement of atoms. For low carbon steels, under normal conditions, austenite cannot exist at room temperature. When steel is cooled slowly, the atomic orientation transforms from austenite into a combination of ferrite and cementite. We call this combination of ferrite and cementite pearlite. Ferrite is nearly pure iron and it's stable at room temperature. We just said that up to about 2% carbon can fit within the gaps of the austenitic structure. Ferrite is nearly pure iron and it's stable at room temperature. We just said that up to 2% carbon can fit within the gaps of the austenitic structure. In the ferritic structure, at around 725 degrees C, a maximum of only 0.02% or 0.02% carbon can fit in the gaps between the iron atoms. But at room temperature, only 0.008% of carbon, or 0.008% carbon, can fit within these gaps. 100% iron is very soft. Ferrite at room temperature is no more than 80 parts per million carbon, so that's really close to pure iron. When we're discussing ferrite, you should think of something soft, low strength, and very ductile. We see this on the global formability diagram, and that compares tensile strength on the horizontal axis with elongation, a measure of ductility, on the vertical axis. And we find these interstitial free or IF steels in the upper left-hand corner, representing really ductile but low strength options. If additional strength is needed, then more alloying elements must be used in addition to carbon. The next most cost-effective alloying element for strengthening is manganese, and when we add that with carbon, produces higher strength steels known as carbon manganese steels. These grades have limited ductility, especially at higher levels of manganese and carbon, so they're used for structural applications that really do need strength, but they don't rely on ductility. So for that reason, we also call these steels structural steels. Around 1980, steelmakers rolled out a new approach to get to higher strength levels while minimizing the loss of ductility that usually comes when we go to higher strengths. They accomplished this by strengthening the ferrite through the addition of very small amounts of titanium, niobium, or vanadium so that carbides or nitride precipitates are formed. These precipitates strengthen the ferrite and keep the grain size very small. We call these microalloyed grades high strength, low alloy steels. Future episodes of this blog series are going to discuss another important phase called martensite and how martensite can contribute to creating the advanced high strength steels. But for now, that wraps up our video blog. If you want to learn more about advanced high strength steels, please visit ahssinsights.org. I'm Danny Schaeffler with Engineering Quality Solutions. If you want to learn more about the services that we provide relative to sheet metal forming, troubleshooting, or training, please visit eqsgroup.com. Thanks for watching and have a great day.